Comparison of various modulation schemes for transmitting audio signals. A proposal by Auspland and Matthew Blanchard. For this project, we will be doing an analysis of 3 different types of modulation schemes over various audio bands. DSB-SC modulation, frequency modulation, and phase modulation are the methods of modulation we will be using. To create a sense of realism, we'll also be using an additive white Gaussian noise applied to each different signal. We will do an analysis and comparison of the signal-to-noise ratio, energy efficiency, and cost effectiveness for each of these schemes. And we will test these samples using different instruments such as percussive instruments, wind instruments, and other different types of sounds.
The transmission scheme for the various audio signals can be seen in the image to the left. Audio signals for a variety of instruments will be tested, including percussion, brass, wind, and string. Each audio signal will be modulated across 3 different types of analog modulation, including phase modulation, frequency modulation, and double sideband suppressed carrier modulation. At the channel, additive white Gaussian noise will be injected, and then the signal will be demodulated. Once the signal has been demodulated, it will be analyzed for signal-to-noise ratio and energy efficiency, and the 3 modulation schemes will be compared to see which one is best for that instrument or audio band. The viability for transmitting portions of a single complex audio signal over multiple modulation schemes will be considered. In such a scheme, a single complex audio signal which contains multiple instruments could be divided into separate audio bands via filtering, and each audio band could be transmitted separately on its most efficient modulation scheme. To verify this, a combined audio signal could be used rather than a single instrument. Filtering could then be simulated on that audio signal in order to separate the various instruments. Each instrument could then be transmitted using its preferred modulation scheme as found from the earlier study, and then recombined at after the demodulation stage. The signal-to-noise ratio and energy efficiency could then again be examined to verify our findings earlier.
The entire project will be built and analyzed using MATLAB. To create a sound file, there are 2 methods normally used. The first is sampling, where we can record an instrument and operate on that signal we record, or what we are going to use, waveform synthesis, where we create a waveform using different combinations of predetermined waves. Most of the remaining operations that need to be done already have pre-built blocks using Simulink and MATLAB. This includes all the different current types of modulation we have, the additive white Gaussian noise, and the signal-to-noise ratio.
The scope of this project leaves much room for growth, and many add-ons can be made during this course of the project, if time allows. Some examples of possible additions include examining digital modulation schemes for audio. In such a scheme, the audio would first be converted to a digital signal through a digital-to-analog converter. The digital signal would then be modulated using a digital modulation scheme such as BPSK or QPSK. The various orders of phase shift keyring could be compared for their baud rate and bit error rate for various audio bands. Different carrier frequencies could also be used for both the digital and analog modulation schemes. The signals can then be compared for signal-to-noise ratio and energy efficiency, same as before. More analog modulation schemes in addition to the 3 outlined previously could also be explored, such as vestigial sideband modulation. More instruments could also be examined using the same procedure outlined originally, including instruments from different audio bands and different combinations of instruments.